Hi, everyone. First, I'd like to thank Marina and the organizers for the opportunity to give this talk. And so essentially, I want to tell you about a simple lattice model that has spin and orbital degrees of freedom that you construct on a honeycomb lattice that had some sort of fractonic behavior. And here's my outline. I'm going to start with some general remarks about quantum spin liquids and fracton phases. I'm aware that fractons were discussed in the lectures last week and also previous talks. So I'm going to be brief here, just say some very basic things to make some analogies with the model that I'm going to discuss in more detail later. And our motivation for constructing this model is going to come from effective models for Rydberg atom arrays, where you have this spin and orbital degrees of freedom I'm going to explain. And we're going to interpret the ground state degeneracy of this model in terms of symmetries that act on subsystems. And at some point, I'm going to add some perturbations to turn this model into something with a fractonic behavior. And I'm really going to focus mostly on the lattice model, but in the end, I'm going to make an effort to try and bridge this gap that we have been talking about at this workshop and tell you a little bit about what we understood about taking the continuum limit in this lattice model. And this is work done in collaboration with William Nattori from Campinas, and Wesley and Fabrizio are two Brazilian postdocs in Taiwan. So first, quantum spin liquids are spin systems that avoid long-range magnetic order at zero temperature. And the reason why this happens is because you have some strong interactions and quantum fluctuations that really destabilize in kind of a symmetry breaking state. And what you get is more exotic. The paradigm that you have here is this RVB, or Anderson's resonating valence bond state. The picture is something like this. You take, say, the triangular lattice, and you form singlets between pairs of neighboring sites. And you take a sort of dimer coverings on this lattice, and you construct a coherent superposition with all the combinations that restore the symmetry in this state. So this would be a quantum many-body state that does not break any symmetries. But it has very interesting properties. So, for example, if you try to look at the excitations on top of this state, you realize that they are fractional in the RVB picture. What you can do is to break a singlet and form these two spins 1/2, and there is no energy cost for separating these excitations on top of this highly entangled ground state. So you say that these are spin 1/2 excitations that are deconfined, and they're called spinons. And another reason why these quantum spin liquids are interesting is because if you get, for example, like what happens in the RVB state, if you have a gapped quantum spin liquid, you get a topological order. So that's guaranteed that your fractional excitations are also going to have some fractional statistics. They can be anyons, either abelian or non-abelian anyons. So one famous example here that is going to be useful for what I want to talk about is the Kitaev spin liquid. This is defined on the honeycomb lattice. So you take spin 1/2 degrees of freedom here represented in terms of these Pauli operators, and you put spins 1/2 on the sides of the honeycomb lattice with these two sublattices painted here, the sides in different colors. And you label the bounds of the honeycomb lattice as X, Y, and Z, depending on the direction. And you add this interaction that it's sizing-like, but the components you put in the interaction depend on the direction of the bound. So these are like anisotropic bond directional interactions. And this is a model that Kitaev proposed back in 2006, and that has generated a lot of interest in condensed matter physics, because even though it looks sort of artificial, it can actually happen in real materials that people started calling Kitaev materials, where this interaction can actually be dominant. One reason why Kitaev proposed this model is that it's actually exactly solvable, and you can show that it has a spin liquid ground state with some Majorana fermion type of excitations. So the reason why you can solve it has to do with the fact that this model actually has an extensive set of local conserved quantities. You can take these plaquette operators, so choose a hexagon on the honeycomb lattice and label the sites like this from 1 to 6, and you take products of Pauli operators with the component that points that you choose as according to the bond pointing outward from that site. So for example, site 1 is the sigma z. And you can check explicitly that this plaquette operator is commute with the Hamiltonian. So you have one conserved plaquette operator for every unit cell of the honeycomb lattice. And then these are actually Pauli operators. They square to 1, so the eigenvalues are plus or minus 1. And it's exactly known that by a theorem due to Lieb that the ground state here lives in the sector where you fix the eigenvalue to be plus 1 for every plaquette. And then you can talk about, you can also find the exact excited states and talk about the excitations in this model. And they can be exactly solved in terms of this Majorana fermion representation. You basically write the Pauli operators as bilinear of Majorana fermions. The C here, they actually act as mobile or itinerant Majorana fermions moving on this honeycomb lattice, and the B's are combined to form Z2 link variables that are effectively like a Z2 gauge field. And this plaquette operator that I was talking about is actually like the effective flux for this Z2 gauge field. So in addition to Majorana fermions, another excitation you have in this model is that you can actually flip the sign of the eigenvalue of a plaquette operator from plus 1 to minus 1, exciting your Z2 gauge field. Then that's like a vortex for these Majorana fermions moving on this lattice. For the Hamiltonian, as I wrote, actually the fermions are gapless, the vortices are gapped, but you can actually perturb the model with a magnetic field and gap out the fermions as well, and what comes out is some kind of a non-abelian quantum spin liquid where the Majorana fermions, vortices, they can form bound states with fusion rules of the Ising model. And even more exotic than quantum spin liquids are fracton phases. So this comes with a number of interesting properties that we heard about in previous lectures and talks. So one very important thing about fractons, you get this excitations with restricted mobility. Isolated excitations can be immobiles. These will be the fractons of the theory, but you can form mobile excitations by forming bound states. These are the dipoles that will have also restricted mobility in the sense they can only propagate along certain directions of the lattice. Also, you have subextensive ground state degeneracy, meaning that typically the ground state degeneracy will grow exponentially with a linear system size. And this is something that people started calling fracton order. It's similar to topological order in the sense that this ground state degeneracy is robust against local perturbations, but it also depends on geometry in the sense that it will depend on the length scales, the size of the system in your lattice. And to make sense of the effective field theories that have been worked out for fracton phases, you always need to bring in some microscopic length scale. That this has been called the UV-IR mixing. So just to give one example here that I like because we worked on this model, this is the Chamon code. Typically, these spin models, the lattice models that have fracton behavior, they involve these multi-spin interactions. In this case, the interactions of the Chamon model are defined on this octahedra. So you take the 6 sides on the octahedra and define, this is like a stabilizer code. This is the local stabilizer, and you sum this over all the octahedra covering some FCC lattice. And then you can show, for example, that the ground state degeneracy here will grow exponentially with this number n. which is calculated as the greatest common denominator of the linear system size along x, y, and z directions. Right, this is something you can get from the lattice model, but also from effective field theories, and which are also very, very useful. These are Chern-Simons-like effective field theories for these fracton phases. And one thing that we did using this kind of theory some couple years ago is that you can actually use some analogy with quantum Hall effect and then derive boundary states by imposing that geometry's open boundaries are invariant under gauge transformations. Then you have to add some physical degrees of freedom of the boundary and describe the boundary modes for fractal models like the Chamon code. But what I want to talk about is really some analogies that people have been making with fracton physics in classical spin models. What I mean by this is that these are Ising-like models or plaquette Ising models. You can think about them as like just writing some classical Hamiltonian in terms of Ising variables that implement some constraints that select some configurations that form your ground state manifold. And then the defects will be violations of these local constraints. And these defects can have this fracton-like behavior. They'll be localized in the sense that you cannot move them without creating additional excitations when they are isolated at the corners of some membrane operators. So the first example here is just this plaquette Ising model on the square lattice that was proposed in this paper. Here the spins live on the centers of the squares. So if you create, if you flip a single spin, you actually create 4 excitations. But if you start flipping spins along a membrane, you can isolate these excitations, and then you can try and convince yourself that you cannot actually move this excitation here in yellow without creating additional excitations by starting to flip the spins. Another example is this, it's also some kind of plaquette Ising model on the triangular lattice. It's also called the Sierpinski triangle model, because you start flipping spins and you create excitations that live on 3 triangular plaquettes, but then you can start separating them, creating these membranes, and you can place your excitations at sites that corresponds to some Sierpinski triangle. And more recently, there was this one on the honeycomb lattice. This was called the Ising fracton spin liquid. It's defined in terms of this operator here, some combination, summing over these Ising variables around the hex. There's an inner hexagon and the outer hexagon with some fine tuning of these parameters here. And then you square this thing to implement some constraint that selects some configurations. And there also you can show that you get these fracton-like excitations and also dipoles that you can form at the edges of these ribbons that will only propagate along some directions of the honeycomb lattice. And so these models have some fracton-like physics. It doesn't have fracton topological order in the strict sense that they're not going to be robust against all kinds of local, the ground state degeneracy is not robust against all kinds of local perturbations. And some of them can have this subextensive ground state degeneracy I was talking about, but others do not. So for example, this one does have this subextensive ground state degeneracy. This one here does not, because it has some local conserved quantities. The degeneracy is actually extensive, grows extensively with the system size, exponentially in the system size. And this one's more complicated because it's fractal, but okay, so we thought it would be fun to try and add to this list of classical models with fracton-like physics. And our motivation for constructing this model comes from this paper that discusses a lot of different quantum spin liquid phases that you can get from Rydberg atoms on the Ruby lattice. So the degrees of freedom here are these Rydberg atoms. You can think of them as some kind of 2-level systems so that you can excite. So there's a ground state and a Rydberg state. When the atom is in the Rydberg state, it has this extended wave function. You can have very strong van der Waals interactions between these Rydberg states in a way that if there is another atom within some radius, it's called the blockade radius of an excited state, it just costs too much energy to excite the second state, the second atom to the Rydberg state. So with that, you start playing games with like the possibility of exciting one atom depends on the state of the other atom. And the effective interactions that you get for Rydberg atoms look like this. So basically, you have van der Waals interactions that decay very fast with the distance. So so if I put this is the Ruby lattice, and if I can engineer the parameters in a way that the interaction is very strong within this blockade radius. So basically, if I excite this atom in black, it will block the other atoms in the vicinity to be in the excited state. So this would be in the ground state. This would be this U here. But you can also get, this is like truncating this long-range interaction to the next nearest neighbors. So you can also get these interactions between atoms that live on these rectangles here. And this delta parameter is the detuning of the laser that will drive transitions between the ground state and the Rydberg state. This is in this Rabi frequency term. Sorry. Yeah, so this would be this Rabi term. And so we're going to work in this Rydberg blockade limit where I'm going to take U to be infinity, but we keep this interaction V between states on the atoms on the rectangles. So in this case, you can see that actually on the Ruby lattice, you get only 4 states per triangle, which are shown here. So this will be our this will define our local Hilbert space that has 4 states. And also notice that the Ruby lattice is actually it's constructed like putting triangles on top of the honeycomb lattice. And here I'm going to use the analogy with the Kitaev model to label the bonds in the same way. This will be useful in a minute. And also we're going to assume that this Rabi frequency is very small and work in this limit where you just have the interactions between Rydberg atoms. So this is going to be a classical model, okay? Okay, there are many different ways to represent this model and the degrees of freedom. I'm just going to mention a few of them. So first, if you take the 4 states that I was talking about, you can basically flip the triangles upside down, and where you have the atom in the Rydberg state, you actually represent as a dimer bond here. It's like a singlet living on this bond. You do this for all 4 states. And in this way, you can relate this kind of model to dimer coverings. You connect these triangles in this way to form a Kagome lattice. So this is like dimer coverings of the Kagome lattice. And also, if you like, you can represent this in terms of arrows that point in when you have a bond, when you have a dimer on a given bond. Right, and in this case, it looks like some kind of Kagome spin ice with these 4 states. And what I'm actually going to use is this representation here. I'm going to explain more in the next slide, where the arrows, let's see, the arrows that point outward will be minus signs, and pointing in are plus signs. Because of all these possible representations, this model has actually been studied before in the context of dimer coverings of the Kagome lattice, and it's known that it has an extensive ground state degeneracy that grows like this exponentially with the number of unit cells. So what we're going to do is to map this model to spin and orbital degrees of freedom. So I'm going to represent the 4 states this way. So these plus and minus signs will correspond to eigenvalues of some operators that commute with each other. With this constraint, because I have these 4 states, the constraint is that the product of all 3 signs has to be -1. And because I have a local Hilbert space with 4 states, that actually can be written in terms of 2 pseudo spins 1/2. So I'm going to use something I'm going to call the spin degree of freedom sigma, and also an orbital degree of freedom. This kind of model appears in condensed matter in the context of so-called Kugelkomsky models, where actually this what happens there is that usually the spin exchange interaction depend on the orbital state, so you get some interaction that involves both degrees of freedom. And you can represent all the operators in terms of sigmas and taus that obey the usual ST2 algebra. They commute, sigmas commute with taus and so on. And all the interactions that I showed you before can actually be written in terms of these operators that are products of sigmas and taus with the same component along the gamma here will be x, y, or z. Right? With this constraint that just comes from the Pauli algebra that the three A's multiply to -1 on every site. And these labels here for the states are just the eigenvalues of all these three operators. So using this representation, you can rewrite the interactions in this between Rydberg atoms on the Ruby lattice this way. So you get this interaction term with some coupling constant J, which is antiferromagnetic-like for these operators because it comes from the repulsive interaction. And you get this kind of term, which is just linear. It's like a longitudinal field in analogy with the Ising model in the sense that what shows up here actually commutes with all the operators in the interactions. The transverse field-like term would come from the quantum fluctuations that we are neglecting. Yeah, sure.
This is actually four-dimensional.
Four-dimensional.
Should I think that you're adding an extra constraint to get rid of one of the states?
Yeah. So no, I do have all four states.
Oh, there's the empty state.
There's an empty state, yes, that's right. I'm going to call that the zero in a moment, and I'm going to change again and be hopefully more clear. Okay, so in this representation, you can think of there'll be a lot of ground states. I already told you that there are going to be exponentially many, and the ground states are the configurations where you obey this. Okay, so first I'm going to choose to tune the detuning in a way that I can cancel this longitudinal field just to simplify the description. This is not really crucial for what the properties we'll get afterwards, just like a longitudinal field in an antiferromagnet like system. So let's get rid of this, and then we'll just focus on this interaction. For short, we call it the spin-orbital Kintaev model because it has this additional orbital-like degree of freedom. But it's classical, right, because everything here commutes. And the ground states are the states that satisfy this constraint on every bond. So just to show you one ground state, you can look at this and just check that if you have a plus here on the Z bond pointing up, you have a minus on the Z bond, so they always multiply to -1. Okay, so what about the symmetries of this model? We're going to use this to count ground states, the result I told you before. So basically everything is constructed here in the Hamiltonian in terms of these operators. And one thing you can do, by analogy with the Kintaev model again, is that you can take this product of the A's around the hexagonal plaquette with the same labels X, Y, and Z that I showed you before for the Kintaev model. And actually, because you have this constraint that all three A's at every site multiply to -1, you can actually rewrite this in terms of products of A's around the bonds. And this will be always +1 in the ground state sector. So here there's also an analogy with the Kintaev model in the sense that the ground state sector is defined by having this uniform flux-like of this plaquette operators eigenvalue +1. But also you can change the signs because you have the sigma and tau operators, and if you take, for example, the sigma z operator, it anti-commutes with ax and ay. So if I apply sigma z to one side here, actually change two signs. But you can use this to construct another plaquette operator that is also conserved, which is just take, instead of taking products of A's around the plaquette, you take products of sigmas or product of taus with the right components as before, and then basically you flip the signs that are inside the plaquette here, but in a way that you still respect the constraint on the bounds, right? So this will actually give you plaquette operators, sigma, W sigmas and W taus, that commute with this Hamiltonian for this spin orbital model. They're not really independent because the product of this is just the W way that I was talking about before. So we have these plaquette operators, the W sigmas on every plaquette. But there are also other types of conserved quantities here that are not obtained by multiplying, by taking products of the plaquette operators. These are these line operators that you can define. These are non-contractible lines. If you have periodic boundary conditions, they wide around the torus. So you can take this one, for example, apply sigma z's along this line. This is run along X and Y zigzag lines of the honeycomb lattice. And you apply I call this line Z because it's perpendicular to the Z bond, and you wind around the torus. So this also commutes to the Hamiltonian. This line, you can take a line that runs this way and also similar along X and Y directions that wide around the torus in different ways. And these lines are actually, you can move them or deform them by combining them with plaquette operators. So for example, we start on this one and apply the plaquette operator, I can stretch this line down this way. So these lines are topological in that sense. Right? So, and what you get here is that to count the total ground state degeneracy, I need not only the local plaquette operators, these are local conserved quantities, but also these non-local lines that wind around the torus. And this is in a way similar to Z2 topological order, like in the toric code. And if you put all of this together, you can count the ground states because you can choose one of those configurations that obey the constraints on every bounds and choose to apply or not the plaquette operator to flip some signs. But there are, here it's important to note that there is a constraint between all the plaquette operators that they multiply to the identity. So there are n-1 independent plaquettes on the lattice with n unit cells. But we also have this, two of these contractible lines if you wind around one direction or the other direction. So there are two more signs that you can choose here for applying or not the line operators. So in total, you multiply this, you get the ground state degeneracy that I mentioned before, right? Which is going to be extensive in the number of unit cells. And you also can convince yourself that if you create this string-like operators, like open strings, you're going to get excitations, which are bonds that violate the constraint at the end of these open strings. And these strings I can deform in any way by applying the plaquette operators. So far, no fractons in this model. The excitations are mobile, and I get extensive ground state degeneracy. So we wanted to try understand what do we have to add here. Some kind of perturbation that selects some states within that highly degenerate ground state manifold that will give us this Fracton-like behavior. So so here's what to go forward, I had to simplify this notation. So we have 4 states, and one complication was that the model had this anti-ferromagnetic-like interactions. But ferromagnetic is simpler because then I can write some uniform configuration. So what we're going to do here is to apply this sublattice rotation. For those of you familiar with the Kitaev and Kitaev-Heisenberg models, this is the same sublattice rotation that you use to demonstrate some dualities in the Kitaev-Heisenberg model. So you divide the honeycomb lattice into 4 sublattices, and you rotate by pi along one side. You do nothing, just the identity, and the other 3 sublattices you rotate by pi around x, y, or z with this pattern. And in this way, you can actually change the sign of the interaction in the Hamiltonian. So I'm going to use this representation from now on. And this is better because now it's like ferromagnetic-like. So the simplest ground state that you're going to use as reference state is just a uniform state with minuses everywhere. And this minus state I'm going to call 0, so that's the empty triangle. But you can also choose to label the other ones by where the minus sign lives. This will be x, y, and z states, right? And that's easy to remember because now everything, you can act with operators on this basis in the usual way. They'll think like action of multiplying Pauli matrices. Like 0 is like the identity, so we apply sigma z to the 0 state to get the z, and we apply sigma z to x to get y, and so on. And then the action on the plaquette operator on this empty state is just like this. You label the states by x, y, and z. Okay, so and then in this notation, we can kind of understand the perturbations that we have to add to lift the ground state degeneracy. So essentially, we want to get rid of this local, the conservation of the plaquette operators because they're responsible for the extensive ground state degeneracy, but we want to keep the lines which are rigid. We don't want them to be topological anymore. So this will give us some constraints on the mobility of the excitations. So and this is really by design. And here I'm really, yeah, sure. In this case, let me go back to my example here. No, because if so let me think about this. So, sorry, she asked if the plaquette and line operators commute with each other. I'm trying to remember. So if you take... no, they do. So let's try to find a good example here. So because basically it's just the action of flipping the signs in a way that the order does not matter. Okay, so where is my... So for example, so yeah, in this case, I take the plaquette operator. You take it from this state to this state, and then if I could apply a line operator that runs along this zigzag here. So it's like multiplying by z's here. And then I turn zz to 0, zy to x, and so on. So that should be okay. Yeah? So, yeah. So, but in the end, I wanna the bottom line is that I want to construct some line operators that do not commute among themselves. So I get a non-trivial algebra if that's what you're looking for. Yeah, that'll come in the end. Yes. Yes, so this is really by, so we're going to add some perturbation here, which is really by construction, so I'm kind of stepping away from experimental reality because we're going to need some four-site interactions, which I don't know how to realize with Rydberg atoms, which only had two-body interactions. But basically, one way to construct this perturbation is that you can select the configurations that commute with these rigid lines that we want to keep as conserved quantity, but not with the plaquette operators anymore. So basically, you draw everything that is possible, starting from this empty state. If you take lines running along z and x directions. So these are all of them. So the ones in the bottom row is basically the one you obtain from the top row by applying z's along this this direction. So and there are some relations for applying line operators along the x direction as well. So you basically write down a projector that will select these configurations that I like, right? So this is the perturbation, essentially. In terms of the operators I was talking about before, these A operators, it can be written like this. Actually, here I'm dropping some terms that were already there in the original Hamiltonian, but you see that there are four site interactions with position labels like this for the defined on both sublattices of the honeycomb lattice, right? So you basically add this as a perturbation to the original Hamiltonian, and then now this will break the conservation of the plaquette operators, but we still have these rigid strings that commute with the Hamiltonian, and now you can label the states in the ground state manifold by the presence or not of these strings, of this line operators, by the action of these line operators. One important thing here is that actually, so here's one example. You start from this uniform empty state, you apply a Z line along this Z line operator along this direction here, and an X line operator along here. Notice that where they cross, you don't actually get the identity, but you get the Y state, right? Because you have the four states. So in this sense, these lines here are different from other models with subsystem symmetries, where you have some constraint that all the lines or all the symmetry operators have to multiply to the identity. Here, if I apply all the lines, you actually get the uniform Y state. And that's important for counting the ground state degeneracy. In the end, we'll scale like this, basically with the number of these rigid lines that we have on the lattice. And then we can work in this limit here, where this perturbation lambda is small compared to the interaction parameter that I had in the initial model. So in this way, the low energy excitations will be defects of these four site operators. There are also the other types of excitations that violate the constraints on the bonds, but those live at higher energies. And then you can basically start with the uniform configuration again and ask how many excitations you create by applying the plaquette operators. And then in this case here, I apply a single plaquette operator again. And I'm coloring in yellow. This region here is it's like a unit cell of the honeycomb lattice that will contain this some four site links where the center actually contains some terms that violate the constraints from this perturbation. This will be our defect. So the single plaquette operator actually create four defects. But one thing you can do here is kind of start applying more of these plaquette operators to stretch this thing. So you apply these Z lines along this direction. So you send the two of these defects away, and what you get here is it looks like a ribbon with two of these defects at the end. This is like the line or the dipole at the end of this ribbon. And if you applied some plaquette operators on this membrane and you send away the other three excitations, you would get the single fracton here living at the corner between this Z and X lines, and you can look at the interactions again and convince yourself that you cannot move these excitations without creating additional defects by applying other operators here. Okay, so finally, let me talk about how we can take the continuum limit in this lattice model. And to do this, I'm going to use some representations of these operators in this four-dimensional Hilbert space. First, we write these operators in terms of Dirac gamma matrices. We choose this representation here in terms of the sigmas and taus that we had originally. So these are gamma matrices. They obey the Clifford algebra. And the AX and AY and AZ operators that were contained in my Hamiltonian are written this way in terms of gamma matrices. And to go to the continuum limit, we use this mapping to bosonic fields. This is similar to what people use to derive effective field theories for Fracton models, or for example, even in topological order, to go from the toric code to the BF theory. So basically, you bosonize your operators. Here we have to do this for this 4x4 gamma matrices by introducing 4 bosonic fields per site. And you write this gamma as the exponential of bosonic fields that depend on this antisymmetric K matrix with some coefficients here that are chosen in a way to respect the algebra of the original operators. Okay, and then you can do this by imposing canonical commutation relations for the bosonic fields in terms of this K matrix. And here I'm going to take the continuum limit in this way. You take this bosonic field to this curly A fields, which is not the same as the A's that I had before. The notation is a bit unfortunate here. So this would be like the gauge fields in a sense. This representation comes with some gauge structure. And here it's important that actually when I go to the continuum, I have to keep this label. We're working on the honeycomb lattice that has 2 sublattices, so I have to keep this sublattice index new. I'm just going to call it even and odd sublattices. So for every unit cell, there are actually 2 of these fields. And A0 here is just the lattice spacing. We're going to need this microscopic length scale. Oops. So with that, you can rewrite the line operators in the continuum limit. So basically, in the continuum limit, this is the commutation relation that we need for these A operators. And then you can take the sigma operators that we use in the line operators. In terms of gamma matrix, they're like this. So they have the non-trivial action on this ground state is written in terms of this θ1 field. And then if you take the continuum limit, it's convenient to use this coordinate system where I choose these coordinates along the directions of the honeycomb lattice. So in some sense, I have to keep some information about the lattice, about these special directions. So here, x gamma would be the coordinate along the direction of this delta gamma. For example, x3 here would be vertical pointing up. And then I have the other coordinate in the perpendicular direction. So in this way, the z line, for example, is written as running along this x3. I integrate over this x3 bar direction, and I integrate over these fields in both even and odd sublattices. And you can do this for the lines that run along the other direction, the x direction as well. And you define these line operators, again, in terms of combinations of the original fields. And here, actually, if you look at the algebra between these line operators that I'm writing, they actually commute for lines that run along x and z directions, even though the z line involves products of sigma z's and the x line products of sigma x. On the honeycomb lattice, remember the crossing between these 2 lines actually contain two sides, so these lines actually commute. To get some non-trivial algebra, we actually have to define another set of line operators, taking the A operators, the local conserved quantities for my classical model, and then again I rewrite this in terms of this gamma matrix and map to bosons, and then something that is a local conserved quantity here is this exponential of this A. And then now, if I take the relation between this local operator and one of the z lines that I had before, you actually get this non-trivial phase here. Basically, this condition is where the point crosses the line. It's kind of singular in the continuum limit. It depends on this lattice regularization with the delta function over there. But the algebra for the line operators is more well behaved. So basically, you can take another set of lines which integrate now this AX or AY fields here, these linear combinations of the original fields, but it's important that they contain only the fields in one sublattice. Could be either even or odd, so they cross at only one point. And then in this case, you have this new U line operators. I had the V's from before, and then they obey this non-trivial algebra here. And you can get the ground state degeneracy by counting how many of these lines you have, right? So, you can label the ground states by the eigenvalues of the U's, for example. But to count the lines here, as usual, you need to talk about the thickness of this line, right? So you need some lattice regularization. So if I have, if I go back to the lattice, then this will be consistent with the degeneracy that I mentioned before. If I say I have L1 lines in one direction, L2 lines in the other direction, so you get this subextensive ground state degeneracy. Yes. Okay. So basically, I'm done. So let me. Just make some final remarks. So basically what I showed you is just we're trying to construct this classical model that has some Fracton-like excitations on the honeycomb lattice with a starting point that it's at least the starting point is realized in Rydberg atom arrays. It's different from the other models because here I basically have 4 states per site. This is our local Hilbert space. And then, so I started with this motivation for about Rydberg atoms to construct this model. But if you think about the way you construct it actually from a more mathematical point of view, what we did was we can take the Kitaev model where it's defined in terms of sigmas, operators that anti-commute, and I added another degree of freedom that I called orbital in a way that now the interactions are defined in terms of operators that commute, right? So you basically end up with this classical model. You're turning this the original Kitaev model into some classical gamma matrix model, right, in this gamma matrix representation. And this can actually be generalized to other Kitaev-like models that people have defined, which are also exactly solvable in terms of Majorana fermions. You can do this in many different lattices, even in 3 dimensions, where you can put the Kitaev-like interactions and see what you get. I think that this might be fun. And then as an outlook, I mean, it will be interesting, of course, to try to understand physical realizations, talk about thermodynamics. Actually, here there's the issue about whether the systems will actually thermalize, right? Because you have this immobile excitations, the fractons, but at least for one of the models that I showed before, people found a way to do some cluster, classical Monte Carlo that finds a way to equilibrate the state and compute thermodynamic properties, look for finite temperature phase transitions. And of course, it will be interesting to add quantum fluctuations because I start with this gamma matrix like models, classical models. You can add the transverse fields. The Rabi frequency term that I mentioned before will really be like a transverse field, and you can talk about the quantum phase transitions and in this kind of setting as well. So with that, I'll stop here and thank you for your attention.
So your construction starts with this nearest neighbor Rydberg blockade. Do you know like how it will affect the, I mean, it's probably hard to say, but how will it affect the properties if you consider also next nearest neighbor Rydberg blockade, which is more commonly done?
Let me think. As long as it's weak, it shouldn't affect too much the construction. Like if it's strong, then you can probably get to another phase, right? So people have looked into this in the context of Rydberg atoms, like when you have this charge density wave phases, right? And the number of phases that you get depends really on the range of the interactions because if they can break the symmetry in different ways. So here, it will still be classical, but so you got a classical model written in terms of these A operators, but you can probably take this in a different direction, like to select a different subset of the ground states that that has completely different behavior. Really, I haven't thought about it. So,
Okay, thanks. Yeah.
yeah.
So you have a lot of ground states, and they should be locally distinguishable, right? Like you can distinguish among them with.
Here you can distinguish them locally, right? Because all the ground states are actually product states of some of those local configurations that I was drawing. So it's not really like the topological order in that sense, right? The thing is they're not eigenstates of sigma nor tau, but they're eigenstates of the products, right? These are the local quantum numbers.
And can you still make sense of this extensive sub-extensive ground state degeneracy as some SSB of subsystem symmetries?
Yeah, if you like. Yeah, so basically the pictures that you have these line operators, and each of the ground states will have a different eigenvalue for this line symmetry operators. So you can basically.
I see. And you cannot deform these lines into one.
No. They're rigid because when you add this perturbation, you cannot make turns anymore, and so you remove the plaquette operators and cannot make turns.
Thank you.
So, can you elaborate a little bit more about the physical realizations and how do you actually probe the system, in any way to talk about this ground states? And of course, this question coming from a guy who just gave a talk on Majorana fermions is very odd.
Yeah. So like I said, I don't know how to do this. These four-side interactions from Rydberg atoms or again naturally two-body interactions, but perhaps here there are all these different representations of this model, and for example, I mentioned the version in terms of Kagome spin ice. So people have also realized Kagome spin ice in different systems, like with qubits and superconductors. So maybe there is some hope there. But in terms of things you can measure, one thing that we were able to calculate for the original model is I think I have a slide about this, is so these are like spin systems, right? So one thing you usually calculate is the structure factor, so, which in the real material comes from X-ray diffraction. In this case, for the original model, it's actually solvable. So you can do a lot of things. You can compute the specific heat and the zero temperature structure factor by averaging all the ground states, and then it looks like this. This is like the cross section for X-ray diffraction. And one thing you can see here is that there are no Bragg peaks in this, right? So this would be similar to some classical spin liquids or Kagome spin ice in that way. But this was for the original model without the perturbation. We haven't been able to calculate this yet for the model with the perturbation that gives us the fractonic behavior. So this is something that would be interesting to look at also as a possible experimental probe at some point.
So in the case of these other classical models with Fracton behavior, like the Newman-Moore model or the Plaquette-Ising model that you mentioned, we know a procedure, a gauging procedure from which we can produce a model that does have topological order, like the I guess this is the way that Vijay Ha and Fu constructed the X-cube model by gauging the Plaquette-Ising model, right? Do you know how to do that in your case?
No, I don't know. No. Yeah, we made actually. I didn't mention this. I talk a bit about the something I would like to understand better. First is the effective gauge theory for this simple classical model that I didn't talk about much. Because we tried to do this, we did it for the original model, which is not fractonic, so mapping to gauge fields and so on, and discussing the gauge transformations that we have there. But for the complete model with the perturbations, because they're so complicated, we didn't manage to understand what was going on. But that would be something interesting to do here. And then perhaps you can get a really true fractal topological order in some sense. If you start playing this game like they did in the original paper in higher dimensions, yeah.
Okay, more questions? No? Okay, we thank again Rodrigo. So we meet at 2, okay?